Hello, my name is Gary Swiney, and this is CSE 546 Homework 1. In this homework, we are reviewing the linear regression models, KNN, OLS, Ridge, and Lasso for generalization and performance on the same training and testing data sets in order to analyze both user-generated parameter performance and the performance of the regression models as a whole. So the nearest neighbor algorithm has one user-generated parameter, k, or how many nearest neighbors you select. And this can increase or decrease generalization. And the next model, OLS, doesn't have any user-generated parameters. It is a extremely simpler model. In the last two models, Ridge and Lasso, they're both pretty similar. Both of them use a regularization. Ridge uses L2 and Lasso uses L1. The purpose of this regularization is to reduce overfitting of the data, and you'll see in our results there's limited overfitting of the data for Ridge and Lasso. But they both have the same user-generated parameter, which is alpha, which as alpha increases, it will decrease the training value, but it could show increase in the test value. So in KNN, here at nearest neighbor number of 3, in figure 1a, we can see the sweet spot for our test score. This was the highest test achieved of models, and thus KNN from this result can be deemed the best model for the data. To the right of nearest neighbors number 3, we can see training and test scores decrease together linearly. This is a clear example of underfitting of data as k gets too big, and to the left of N3, we can see overfitting where k is simply too small. If we look at figure 1b here, we can see our test output is 0.7046 for our R2 generalization test score, which is the best result of the day. OLS doesn't have any user-generated parameters, and thus only has one output. And again, this is trying to find a linear model closest to the training set to test against. The test score scored a 66.88% or 0.6688. This was an incredibly average result, and even though the model is simpler, which is a pro, it is worst fit for generalization. In the Ridge model, again, it uses L2 regularization, where the squared L2 norm of the coefficients are penalized. The main purpose of this, again, is to reduce overfitting of the model. And again, in the results, you will see that. However, as alpha increases, both training and test scores flatten out until they immediately plummet to 0. So we can see that here in figure 3a. Our alpha sweet spot is somewhere between 100 and 150. I call it right at 125, although others might disagree. It is still relatively the same. Throughout, if this were to extend to the right of alpha equal to 200, we would see the model become more and more underfit. You can already begin to see the trend of underfitting as training decreases here, but this is just a smaller window into the model. And on the left here, we can see a small example of overfitting, but again, it is very small, and as these models, the purpose is to reduce overfitting as much as possible. So at our peak, we found at alpha equal to 125. We got a result of 0.6809, which again is average performance. As you can see here, the testing score does not get any larger in this sweet spot. Our last model we analyzed was Lasso, which instead of L2 uses L1 regularization to push some coefficients to 0, so some features are entirely ignored by the model. There is an automatic feature selection in place, which is not user-generated. Again, the purpose of this model is to reduce overfitting of the data, and as you can see, there is very little to no example of overfitting of the data. our sweet spot was found somewhere between 10 to the negative third to 10 to the negative 1. And then to the right of our sweet spot, right beginning at alpha equal to 1, and as it gets larger, we can see a linear decrease in the training and test score results, implying heavily that the data here becomes underfit. So, looking at our sweet spot of around 10 to the negative third to 10 to the negative 1, we tested at alpha 0.001 for a test result of 0.6688. And again, this is average to worse than average generalization performance, as we can see in figure 4b. So the best performing model that we found today was the nearest neighbors at n equal to 3, with a test result score of 0.7046. And that concludes the presentation. Thank you so much.